Okay. All right. Okay. Well, welcome. I guess welcome to class. All right. It's Wednesday now, and it's only week one, but I'm excited. I'm excited. All right. So today we are going to continue our discussion on the Beta-Binomial model. Okay. And so again, the beta distribution, it's got this PDF, right? It's got this PDF, and when we talk about the beta distribution, the random variable here is theta, okay? If you were to look up the beta distribution, go to beta distribution. You go to Wikipedia, and you look up the beta distribution, and you look up the PDF. Sometimes students get confused a little bit by, can I zoom in on this? How do I zoom in on this? Right? So here's the PDF, and it says x to the alpha minus 1, 1 minus x to the beta minus 1, okay? And it feels a little bit strange because it's using x, but it's the same thing. It's just a random variable, and we often think of our random variable as some value or something, but here, remember, theta, or x, or whatever your random variable is, represents the proportion that exists inside some population, right? So here, the example I used was, inside this pouch are marbles, and some proportion of them are blue, and the rest of them are not blue. And the question is, what is the proportion of blue marbles inside the pouch? It's some percentage or proportion between 0 and 1. Okay, and that's the model. That's the variable we're trying to model. Okay, the other example we've been using is the baseball example. Okay, in baseball, we want to know what is the player's batting average. Batting average is the number of hits divided by the number of at-bats. Okay, and so if a player gets a hit at every single at-bat, their batting average would be 1. They'd be batting 1,000, which just doesn't happen for a season. Could happen for one game. Like a player could have 3 at-bats in a game, and they could get a hit all 3 games, and they would say, they had a terrific game, they've been batting 1,000 that night. Or if they get 0 hits out of all of their at-bats, their batting average would be 0. Okay, so it's some proportion between 0 and 1. Okay, so again, here's the PDF of the beta distribution. This beta coefficient, is made of these gamma functions, okay? And it might feel a little bit intimidating, but again, the only purpose of that coefficient, this value up here, is so that the whole thing integrates to 1 when you take the integral. Okay. What we can say, all right, is we can say, well, okay, if we integrate this whole thing, if we integrate the entire PDF, okay, and it's defined on 0 to 1, right? You can't, this beta, okay, is the beta distribution is just going to be 0 outside of 0 and 1, okay? And so if we integrate this whole thing integrates to 1. That's the property of a PDF. And so what this means is that, if I were to factor out this coefficient, 1 over beta, alpha comma beta, right? This is just a constant. If I were to factor out that constant, what we can say is that this part over here, the integral of 0 to 1, theta to the alpha minus 1, 1 minus theta to the beta minus 1 d theta, we know that this thing must integrate to beta alpha comma beta, right? Because whatever this part over here is, times this part over here, multiplies, well, this thing, whatever it integrates to, this times this equals 1, so this thing must be equal to that, right? So that's going to be a useful relationship. All right, so let's revisit this baseball example and let's work through this, okay? So we said to represent our prior knowledge about baseball, we're choosing a beta distribution with these shape parameters, okay? Now, different people might have different opinions about what distribution we should use for the prior distribution, okay? The blog, okay, because I want to give credit to the blog that I'm basing my lectures off of, decided to use these parameters, 81 and 219, where the mean value is around 0.27, which in my opinion is a little bit generous for a batting average, okay? Probably a batting average closer to 0.25 or a little bit lower than 0.27 is something that I would have chosen, but that's fine. We're using the parameters alpha equal to 81 and beta equal to 219. And again, the relationship between these shape parameters is you can kind of think of it as the number of yeses that you've seen for alpha and the number of no's that you've seen for beta. And thus, we've seen a total of quote unquote, and again, these are like pseudo observations. It's like we've seen a total of 300 observations. 81 plus 219 is 300. And of those 300 observations, 81 of them were yeses or 81 were hits, 219 were not. And therefore, our distribution looks kind of like this. And it's got this, but this is satisfactory to us because almost none of the values are below 0.2. We've got nothing above 0.4. And, the vast majority are under 0.3, which fits kind of our prior knowledge of kind of baseball performance, where we know that as far as batting averages go, most baseball players have a batting average above 0.2, and most baseball players have a batting average below 0.3, and perhaps the greatest baseball players might have a batting average of 0.33, 0.34, but again, very, very, very difficult to have a batting average significantly above 0.3, okay? Again, the highest career batting average ever in the history of all of baseball is 0.366, okay? Something around there, okay? And at that point, they go out to like 5 decimal places to kind of calculate these values, okay? And again, if you are not familiar with baseball, you would have a very difficult time trying to think of what a prior distribution should be, right? So, in all of data science, we emphasize, the Venn diagram I often use says data science is a combination of kind of coding skills, computer hacking skills, coding skills, the ability to write code, your math and stats knowledge combined with domain expertise. And so you need to be familiar with the data that we're exploring, right? And so I recognize that many of you don't know anything about baseball, and that's why I keep explaining all of this stuff, and I hope I'm not insulting anybody by continually explaining baseball here. But you need to have some knowledge about the subject. Otherwise, your analysis will be very, very weak, right? So by using the parameters alpha equal to 81 and beta equal to 219, we'll plug those in our PDF. The PDF is going to be equal to this. 1 over beta function 81, 219, theta raised to the 81 minus 1, 1 minus theta raised to the 219 minus 1. Okay? And so here, theta represents the player's batting average. And again, this is what we're trying to figure out is what is the player's batting average? What proportion of at-bats will result in a hit? Okay, so again, let's say we get a brand new player. Okay, we've promoted this player from the minor leagues. This is kind of their major league debut, right? We're real excited. And, maybe in the first 3 games or first 4 games, they get a total of 10 at-bats, right? They get 10, technically not the same thing as a plate appearance, but they get 10 at-bats, okay? And out of their 10 at-bats, they get 5 hits, right? So it's like the first 3 or 4 games of the season, they have 10 at-bats, they get 5 hits. And so everyone's really excited about this rookie player, this new player, their major league debut. Okay, and so let's see, these are the outcomes, right? We'll say O for out, H for a hit, okay? And so H will be the X is equal to 1, O will be X equal to 0. And so we get, 0, 1, 1, 0, 1, 0, 0, 1, 1, 0. Okay, that's the sequence that we get. Okay, and if we say, okay, the player's batting average is theta, then the likelihood of this exact sequence of data, right? The likelihood of this exact sequence of data is theta to the 5, 1 minus theta to the 5. Okay, because I would do the probability of a hit is theta. The probability of an out is 1 minus theta. We've got 5 hits, we've got 5 outs. Theta to the 5, 1 minus theta to the 5, right? If we wanted to just say, hey, what's the probability of getting 5 hits out of 10 at-bats? The order doesn't matter. We could include the binomial coefficient where you have 10 choose 5 and you have, whatever sequence it has, right? But honestly, it doesn't even matter because these constants, we're just going to chuck them out. Well, not chuck them out, but we're not going to worry too much about them at the moment, okay? All right, so in general, if you have a total of n observations and you have z successes and the probability of a success is theta, then your likelihood of one particular sequence of outcomes is going to be theta to the z, 1 minus theta to the n minus z. And if you wanted to say, well, whatever possible arrangements, then you'd include that binomial coefficient, but whatever, this is what we've got. All right, hope this is okay, right? So far, so good? Let me go ahead and give you your first view quiz answer. Today's first view quiz answer is the letter A. A as in apple. A as in apple is your first view quiz answer for the day. Okay, we are going to use Bayes' rule to get the next part. The next part is we want to figure out what's the distribution of theta based on the data that we've seen, okay? And this is why we call it Bayesian statistics, is because it heavily relies on Bayes' rule. And yeah, if you look at, the history of Bayes, Thomas Bayes was I believe a priest or a monk or something, trying to talk about ideas, but anyway, okay. So this should be familiar. The probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B, right? And this numerator, the probability of B given A times the probability of A, that's just the same thing as the probability of B and A, or A and B, or B intersection A, however we want to call it, right? It's the probability that the events A and B happen together, right? That's what this numerator is. B given A times the probability of A, or is basically, first A has to happen, that's the probability of A, and then once A happens, what's the probability that B also happens? Okay, the probability that B also happens, once we know A happens, is probability of B given A, is going to end up being the probability of A and B happening together, or B and A happening together. So that's the numerator. Okay, so if we label all of these things and we switch up the letters to reflect what we are doing, what we want to know, this is what we want to know. We want to know what is the probability distribution of theta, the player's batting average. This is an unknown quantity to us. What is the probability of distribution of theta given the data that we've seen, given the x values that we've seen? Okay, well, we are going to say the probability of theta given x is the probability of x given theta times the probability of theta divided by the probability of x. Okay, so the probability of x given theta, this part over here, we call this is the likelihood. It is the likelihood, the probability of observing the observed data for a given value of theta. What's the difference between a likelihood and a probability? Ethan? Likelihoods don't have to add to 1, okay? As far as the calculation for just one instant thing, is that you're going to use the same thing. You're going to use the same formula, right? We're talking about a binomial distribution or some kind of thing. We just say, oh, what's the probability of this exact outcome? Or what's the likelihood of this exact outcome? It's going to be like the same calculation, right? But with a probability distribution, if you factor in all possible outcomes, all of those probabilities will add to 1 or will integrate to 1 if you consider all possible outcomes. A likelihood, on the other hand, a likelihood uses the same formula, except we're only looking at one outcome. In our case, we're looking at the outcome of 5 hits and 10 at-bats. We're looking at that one outcome. And so what are the values that we're considering? We're considering this outcome, this likelihood, across all the different possible values of theta, right? What is the likelihood of getting 5 hits and 10 out of 10 at-bats if the person's batting average was 0.1? What's the probability or the likelihood of getting 5 hits out of 10 at-bats if the person's batting average was 0.5? What's the likelihood if the person's batting average is 0.7 or 0.8 or 0.9? Okay? And even if you consider every single possible potential batting average, all of those things will not sum to 1 or will not integrate to 1. Okay, we'll look at this a little bit more. Okay, but it feels a little bit strange because you're both using the same formula or the same equation to calculate your things. But anyway, the likelihood, the probability of getting the observed data for some given value of theta. Okay, we have the prior. We've talked about this. This is the prior probability distribution of theta. Before we even looked at the data, what was the distribution? What did we believe? What did we say was the distribution of theta? Okay, the marginal probability, this is the probability of observing the values in our data regardless of the value of theta. Okay, this is equal to the integral of the numerator across all possible values of theta. This is a pain to calculate. Okay, this marginal probability is often, I don't say the bane of our existence, but it's often a very difficult thing for us to have to calculate. And so a lot of times we just say, I don't want to do it. Okay? And that's okay. It's okay, because we got ways to work around it, right? We say we don't have to do it because we figured out a way to get around that, okay? So anyway, because this marginal probability, this thing on the bottom, as far as, with respect to theta, it's just a constant. This thing is not going to vary with respect to theta. So it's a constant. So oftentimes we just say this part, the thing that we're after, the distribution of theta given x, is just proportional to the likelihood times the prior. Okay. Sometimes I'm talking and I'm just like, is this just gibberish? I hope this is making sense. Okay. I hope this is making sense. Okay, so let's take a look here, right? So we looked at this new rookie player, had 10 at-bats. This player got 5 hits, and we're excited, okay? And again, the reason why we want to do Bayesian statistics is because we're excited about this player, but we're not going to get carried away, right? The frequentist approach would say 5 hits, 10 at-bats, the maximum likelihood estimate of the player's batting average is going to be 0.5, right? 0.5 is what's going to maximize the likelihood of the data that I've seen so far. But we would not say, I think this rookie player is going to have a batting average of 0.5 for the rest of the season, right? We're not that naive to just take these 10 observations and go with that. We want to take into account that, that's just not how it works in baseball, right? That in the long run, it's got to be something a little bit less. But we don't want to also just completely ignore this either, okay? So we're going to use this. This is the likelihood. The likelihood of our data for some value of theta is just going to be theta to the 5, 1 minus theta to the 5, okay? And this will give us the probability of our data for different values of the batting average. If the batting average was 0.1, we'd get a value. If the batting average was 0.5, we'd get a different value. If the batting average was 0.9, we could plug that into theta, and this would say this is the likelihood of getting this outcome, 5 hits out of 10 at-bats for different values of theta, okay? So the prior distribution, we had already talked about this. We said, we're going to plug in these numbers, 81 and 219. We have this, okay? And again, if we just look at the numerator, we're going to take the likelihood, theta to the 5 times 1 minus theta to the 5, and multiply it by the prior distribution. Okay? And the prior distribution is this whole thing. And again, we're just going to say that the posterior distribution, the probability of theta given x, is proportional to this thing. And because it's proportional, I can just ignore constants, right? I got some constant, some mystery constant. I'm just going to ignore this constant. We're just going to say it's proportional. So we're going to say the posterior distribution here is proportional to this product over here. Theta to the 5 times 1 minus theta to the 5 times theta to the 81 minus 1, or 80, times 1 minus theta to the 219 minus 1. All right, is that okay with everybody? Good? If I'm losing, if you got questions, please raise your hand, okay? All right, and so if I combine everything, right, the thetas combined, the 1 minus thetas combined, we get a total of theta to the 85, 1 minus theta to the 223, okay? And we say, all right, our resulting posterior distribution has to be proportional to this. It's proportional to this, okay? It's not a PDF, because if I were to integrate this directly, it's not going to integrate to 1. I need some kind of constant, a normalizing constant, so that when I do integrate it, it's going to integrate to 1. And then if that's the case, then we can call it a probability distribution function, right? Or probability density function, PDF. So what's the normalizing constant here? Okay, well, let's to figure that out, let's look at this, right? So earlier we said, hey, from the beta distribution, back here we said this whole thing integrates to 1, therefore this part over here, theta to the alpha minus 1 times 1 minus theta to the beta minus 1 equals beta alpha comma beta, right? So here we are, we've got this, right? And what we have is we've got this as something that's proportional to our PDF, right? So let's say, okay, what if I integrate this? What if I integrate this from 0 to 1? What am I going to get? Okay, well, if I look at this, right, then we can say, oh, you know what? Theta to the 85, we could call that 86 minus 1. And 1 minus theta to the 223 is 224 minus 1, right? So I'm just using this identity or relationship that we established earlier to say, well, if I integrate this thing from 0 to 1, then it's got to equal this. Okay, is that okay? And therefore, this has to be the normalizing constant, okay? Because if I plug this in, right, if I do 1 divided by this, then this whole thing, this part over here will integrate to this, and therefore the whole integral from 0 to 1 will just equal 1. And so therefore the posterior distribution, after combining everything, right, so we know it's proportional to this, the posterior distribution normalized is this, okay? It's going to be exactly equal to this, all right? And what is this, okay? This 1 over beta 86 224 times theta to the 85 1 minus theta to the 223, this is exactly equal to the beta distribution with shape parameters 86 and 224. Okay. So this is supposed to be exciting. But I just want to make sure that we were able to follow along with the steps, of including, you know, the 5 hits and the 10 at-bats. Where did those numbers go when we included it with our prior distribution of 81 and 219? Okay, so this is my posterior distribution. We can take a look at what we did, all right? So here we did 5 and 10, 81 and 219. But what if we just have generic terms, right? What if we just have the prior distribution has shape parameters alpha and beta, and then we look at data coming from a binomial or a sequence of Bernoulli, okay, and we have n observation and z successes, okay? So we'd say, okay, this is the prior distribution, this is our likelihood, theta to the z, 1 minus theta to the n minus z, And then basically what we would do is we would multiply these two things together. If I multiply this along with this part becomes theta to the z plus alpha minus 1. This times this one gets a little bit, more complicated, but it becomes 1 minus theta to the n minus z plus beta minus 1. Okay? And the normalizing constant over here is going to be beta z plus alpha, comma, n minus z plus beta. It feels a little bit strange, but also not that strange. I feel silly talking. Okay, because the idea here is that, remember, we said the alpha is kind of like how many successes we had, right? So we said we had 81 successes and 219. So we had 81 yeses and 219 nos, right? Or kind of, we can think of this as we've seen, quote unquote, 300. We're pretending we've seen 300 hits as far as our prior distribution goes. We're pretending there were 300 hits, 81 were hits, and 219 were not. And now we've seen this player go to have 10 at-bats, gets 5 hits, and so now the total, quote-unquote, number of hits I have is what? 81 plus 5, 86. The total number of outs, 219 plus 5 outs, right? Because he had 10 at-bats and 5 were hits and 5 were outs. So we're just basically adding the actual observed values to our parameters. And so now we have a slightly better informed model where we've got a total of 310 observations, where 86 are hits and 224 are outs. Okay, we'll explore this, I guess, some more, okay? This thing where the likelihood function, so this was all dependent on the fact that when I took my prior distribution and I multiplied it with the likelihood function, it's like the terms combined nicely, right? When I multiply, like the likelihood function and the prior distribution were kind of the same form, so when we multiply them, the terms combined nicely, okay? That is what we call a conjugate prior, okay? So you're going to hear this term, conjugate priors, for, especially in Bayesian statistics. This just means that the likelihood you're talking about and the prior distribution you're talking about have similar forms that when you multiply them together, they combine nicely, okay? They combine nicely, and the resulting distribution is actually in the same, is of the same form as the prior, right? So here the prior was a binomial, was a beta distribution. We took likelihood from either a binomial or Bernoulli. And then when we combined it, the resulting posterior distribution, the thing that we got after the fact, is also in the form of the beta distribution. So that's what we call a conjugate prior. There's a bunch of examples of these things, right? You can go to Wikipedia, look at conjugate priors. There's a bunch of stuff, but here we have this example. The binomial combines with the beta, right? The binomial likelihood combines with the beta conjugate prior, okay? But then you have other distributions, right? If you have data coming from a Poisson distribution, right? When do we use a Poisson distribution? What? Number of arrivals, great, right? That's a classical thing, right? If the arrivals are random uniform values, okay? You've got random uniform values for like the arrivals, like how many pieces of mail you get, how many people stand in line at the thing. That's going to be a Poisson distribution, right? Okay, and then over here we have a gamma distribution. This is the conjugate prior. All right, so the gamma distribution is a little bit of a stranger thing, but it's kind of it's like an exponential distribution, but taking into account multiple observations and things like that. So anyway, the gamma would be the conjugate prior to the Poisson. You've got these other things. We have a categorical distribution and the Dirichlet distribution. You've got the normal is actually a conjugate prior to itself. all sorts of stuff, right? So anyway, you can read more about conjugate priors, but a very important one is the beta and the binomial working together, okay? So I got a whole bunch of plots, okay? A whole bunch of plots. And to kind of illustrate the relationship between the prior distribution, the likelihood, and the posterior distribution, I'm gonna do this, okay? So the prior distribution is gonna be plotted in red. The likelihood function will be plotted in blue, and the posterior distribution, which is the resulting distribution of the parameter theta after we observe the data, is going to be plotted in black. And and we'll have a plot with kind of all three functions combined. Okay. Let me go ahead and give you your second view quiz answer. Today's second view quiz answer is B. B as in bear. B as in bear. Or Bruin, boy, ball, blue. Second view quiz answer. Okay. Now, one thing is that the likelihood function, I'm going to artificially amplify it, okay? Because the likelihood function actually depends on the amount of data that you see, okay? When you have lots of data, the likelihood of getting that particular outcome for a big set of data is really, really, really low, right? If you have one coin flip, the likelihood of getting heads is 0.5. If you have two coin flips, what's the likelihood of getting two heads? 0.25. If you have three flips, right? And what's the likelihood of getting some exact sequence? Heads, heads, tails. Okay, 0.125. And as you have more and more observations, the likelihood of getting some particular exact outcome gets smaller and smaller and smaller and smaller. Okay? And so I'm going to artificially multiply the likelihood by a constant so that it's kind of on the same scale as the PDFs. The PDFs always have this constant being multiplied because the PDFs always integrate to 1, whereas likelihood functions don't always integrate to 1. So in these plots, I've multiplied the likelihoods by a constant so that it too looks like it has an area of 1, okay? But it's important to note that it's not the true likelihood here, okay? So I'm actually, kind of plotting, I end up plotting the beta distribution instead of the likelihood, but, okay? Likelihood functions don't necessarily integrate to 1. All right, so this is where we start. Let me just shrink this a little bit, okay? So we started with this. This was prior to looking at our data, we had shape parameters 81 to 19, okay? And therefore, most of the values are between 0.2 and 0.3. Everyone's below 0.4. This is kind of what we've established as our prior distribution, okay? This is the likelihood of our data. This player had 5 hits out of 10 at-bats, okay? And therefore, the likelihood is maximized at 0.5. The likelihood is maximized at 0.5. And again, if you did maximum likelihood estimation, your maximum likelihood estimate would be 0.5. But we know that's a naive approach because that's only taking into account the data and nothing else that we know. And again, we know that in baseball, people just don't get to have batting averages of 0.5. So this we would just have to say, oh, this player has been lucky or has been on fire, but not necessarily can't sustain this for the rest of the career, okay? So this is what the likelihood function is, okay? The posterior ends up being a compromise between the likelihood and the prior. And you look at this and you go, oh, that looks exactly like the prior, okay? If I put all three together on the same plot, you'll see that it has actually shifted over a tiny bit, okay? So this blue line is kind of the likelihood, but put on the same scale where, if we were to take the average area of this blue function, it would actually have an area of 1. That's not the true likelihood. Again, the likelihoods don't integrate to 1, but here I've scaled it to kind of for you guys to see. And so you can see the red line is the prior, the blue is the likelihood, and the posterior is a compromise between the red and the blue, okay? It's actually the product. If you were to multiply, it seems strange, but if you were to multiply the red line times the blue line, you would end up getting the black line, okay? And so what's happening here is you're like, what happened here? Well, these numbers are so close to 0, you can multiply it over here that it has no effect, right? They just stay 0, okay? Whereas over here, we see a little bit of slope angling up here, and basically what that has is it shrinks these values down a little bit here, and it amplifies these values over here. And so the product of basically the red curve and the blue curve results in the black curve, okay? The black curve being the posterior, right? And mathematically, that's exactly what's happening, right? We're taking, this represents the red curve, the prior distribution, or maybe I'll go back over here. Where did I go? I'm almost, okay. This is the prior distribution. This is the likelihood. And we're just taking the product between the prior and the likelihood, and we're calling this the posterior, okay? When we multiply the prior and the likelihood, you get something proportional to the posterior. And that's what we have. We're multiplying the red line times the blue line, and we're getting basically the black line, okay? Or something proportional to that. Okay. So again, if I did not amplify that blue line, okay? If I didn't multiply this, so the area under the blue line, the area under the red line, area under the black line, all have an area of 1. But in reality, the true likelihood, and this is just the likelihood of 10 at-bats and 5 hits, the true likelihood, this is the curve, okay? It's just so flat that we can hardly appreciate it, okay? We can hardly see it on the graph. And just so for the purposes of plotting all of these things, I'm multiplying the blue line by a constant so you can see it, okay? And that's going to be especially important when we have larger data sets, okay, or I'm pretending to have larger data sets, because in those cases, the likelihoods get even smaller, okay? Okay, let's just try out another example here, okay? Let's say, all right, so again, we're going to start off with the same prior distribution. Another brand new player, we're going to assume 81, 219. Most players are above 0.2, most are below 0.3, no one's above 0.4. Okay. And now, this player is truly having an amazing start to their season, right? So maybe they've been in 30 games or so. They've had 30 games. They've had 100 at-bats. Okay? They've had 100 at-bats, and they've gotten 50 hits. Okay? 50 hits out of 100 at-bats. This would be major news across in baseball if you had a player who got 50 hits and 100 at-bats. Okay? But this would be the likelihood of this thing. Okay? And so now we have more data, a little bit more of a compelling case, and now we're starting to like, can this player sustain this for the rest of the season, right? 50 hits and 100 at-bats, can this be done, okay? You know, we still kind of doubt that this can be sustained for a very long time, but now we're a lot more excited. We've got a lot more evidence now, not just 10 at-bats and 5 hits, now we have 100 at-bats and 50 hits, okay? So what does the resulting posterior distribution look like, okay? This is the resulting posterior distribution. We can see it has shifted over, okay? We're no longer going to expect the batting average to be 0.2, and now we're like talking about the batting average is most likely to be something above 0.3, and you know, possibly even approaching something in the high 0.3s, right? The high 300s, like their batting average could be as high as like 380 or something, right? This is crazy. And so again, when you plot all three together, you can see the red line and the blue line. And it seems strange, but if you multiply the red times the blue, the resulting curve is going to be this black curve, the posterior curve. Okay. And what do we see? The black curve is taller than the red curve. Why? Yeah, we have more kind of data going into this, right? So prior, we were pretending. We said we're going to pretend, before we look at any baseball player, we're going to pretend we have like 300 at-bats, where 81 of them were hits and 219 were not. And now we've seen 100 more observations. So now that total, right, if we look at the shape parameters, 81 and 219, basically I'm going to add 50 to 81, I'm going to get 131. I'm going to add 50 to 219, I'm going to get 269. I got 131, 269. Those two things now add up to 400, okay? And what we saw, I think, if we remember, on Monday, we saw that when alpha and beta add up to a low number, it's more spread out. When alpha and beta add up to a bigger number, it gets more and more pointy, taller, less spread, okay? And that's what's going on. We basically have more data to back up our kind of feelings about the batting average. And so it gets more narrow, which means it also gets more pointy, taller, okay? And so now the posterior distribution has a mean something closer to something around 0.33, okay? Is that good? Okay. All right, let's say we have a different prior distribution, okay? So this is a different player who we've seen maybe 1,500 at-bats, okay? So this might be a player that we've been following for a while. They've had 1,500 at-bats, you know, been in the major leagues for a few years now, okay? And their kind of career average thus far is 0.27, okay? And we're going to say we've got alpha is 405, beta is 1095. Okay, so we've got a lot of data for this player, and therefore, what do we believe to be this player's true batting average? You know, we're quite confident that it's around 0.27. It's very narrow, it's very tall at 0.27. Okay? Okay, let's say this player who's been successful in the past hits a slump, okay? They've had 100 at-bats, and for the past 100 at-bats, they've only gotten 20 hits, right? So their batting average for the past 100 at-bats is only 0.2, okay? So is this just a slump that we can kind of shake off? Or is this, you know, maybe an indicator that the player actually is not as good? I don't know, right? There's a lot of things to kind of factor in, and so maybe a simple beta binomial model is not sufficient because, you know, we're not factoring like time, right? Like Albert Pujols, he's like old now, but you know, like players age and their performance isn't at their peak levels anymore, right? But we could see this, right? And so if we assume that, you know, batting average is this thing that stays constant, and every instance, every plate appearance, or every at-bat is kind of this Bernoulli thing, which might not be a good model. It's a very simple thing. We could still kind of model this, right? So here, prior, we're confident that something around 0.27. Here, our data says, you know, maybe it's a little bit, the data comes in, the batting average is 0.2 in our likelihood. And so the posterior distribution gets, is shifted a little bit, okay? And this is the result, okay? Here's the prior in red. Here's the likelihood of 100 at-bats. And the posterior is just shifted ever so slightly, okay? And that's because the prior distribution was so strong, right? There's so much that seeing only 100 at-bats in comparison to kind of this player's career is not enough for us to suddenly say you're trash, okay? But if that slump is sustained for many, many at-bats, and I think this is something close to, say, like 1,000 hits or something, okay? So if that slump of having only getting a batting average of 0.2 is sustained for like maybe a few more years, then it will have an effect, okay? So back here, when the slump is, only 100 at-bats, but I forget what number I used here. I think something closer to 1,000, okay? Then the posterior distribution is affected and it is shifted further down here. Okay. Does that kind of make sense, what's happening here? Okay, and one thing to note is basically what the prior distribution is kind of also affects like what could be considered, okay? And we did not draw this example, but what if someone's prior distribution? How do I do this? No, this is not what I want. Okay, I just want to draw on this thing. How do I draw on this thing? Full screen snip, is that what I want? Okay, I guess. All right, what if we weren't talking about a baseball, okay? What if your prior looked like this? It's just a vertical line. Like this is like a coin flip. Prior to seeing the data, right? Somebody says, hey, I've got a coin. What do you think is the probability? Oh, I thought I had a coin in there. What is the probability that this coin lands heads, right? And you say, well, coins just land heads with probability 0.5. And like I flip it 1,000 times and I get something different from 0.5. I don't care. All coins just have a probability of 0.5, right? Somebody says, that's the laws of physics. You can't, if you have a coin, it's going to land with probability 0.5. I don't care what you do, right? The coin is going to land 0.5, okay? So then in that case, basically everywhere else has 0, and you have kind of this infinite mass at 0.5, okay? And in that case, basically, no amount of data, right? Your likelihood can come in somewhere over here or whatever, but when you multiply it by 0, it's just going to zero out. So no amount of data can convince this person that the coin has a probability other than 0.5, okay? Perhaps not talking about coins, but we could talk about like philosophical or religious debates, right? So some people will say, this is what I believe, and no amount of evidence can convince me otherwise. That's fine, okay? But it also just means don't waste your time with a debate with this person, right? Because if they just say, hey, this is what I believe, no amount of evidence will convince me otherwise, then that you just take that at face value and just say, okay, well, there's no sense in trying to debate with this person because no amount of evidence is going to shift their thing. The posterior will be exactly the same as the prior if they assign basically prior to any evidence, the probability of anything else is 0. The posterior will still have 0 afterwards, okay? But anyway, this is just kind of supposed to illustrate the relationship between the prior distribution, the likelihood, and the posterior and how they kind of interplay. And basically, I think in your homework, you're going to be dealing with this, and we'll take a look at some more of this on Friday as well. Let me go ahead and give you your last view quiz answer. The last view quiz answer for today is the letter E. E as in elephant. E as in elephant is your last view quiz answer for today. All right, that's it. We'll see you guys on Friday. Have a good day, have a good evening, and we'll see you guys later.